Hey, okay, welcome back. Today we're going to be talking about a concept called uncertainty. Now, when we talk about uncertainty, what we're talking about is measuring something experimentally. We're going out and we're measuring something. And when you do this, you're going to discover that no measurement in real life is perfect. No such thing as the perfect measurement. Okay, now what do I mean by this? Well, let's do a sort of simple example. Let's say I've got a table. Okay, so we've got a table here. We've got some legs. Okay, here's our table. Right now, what we're trying to measure is the length. Okay, we're going to measure the length of this table. And let's say I have a tape measure and I take it out and I measure this table and I measure it to be 2,315 millimeters long. Okay, so on my tape measure, I've got marks for every centimeter and I've got marks for every millimeter. So I can measure 2,315 millimeters. Now, is this exactly 2,315 millimeters? Is that the exact length of this table? What I mean to say is this equivalent to 2,315.0000000 repeating forever millimeters? And I think the answer that you can clearly see is that no, it's not. This is not equivalent, right? I cannot measure something smaller than 1 millimeter because my tape measure doesn't have marks smaller than 1 millimeter, and my eye cannot see things very, very, very small. So I cannot measure to the precision of a micrometer or a nanometer. It's just not possible with my equipment, with my experimental setup. It's not possible for me to measure the table that precisely. So how do we encapsulate this uncertainty in our measurement? Well, what we do is we can write it down. We can say that it's 2,315 millimeters plus or minus maybe around 1 millimeter. Okay, so I don't know the exact precise to infinite decimal places number. I know it's around this number. And this plus or minus some amount here is what we call the uncertainty. Or we can also call it error, okay? So the true value is somewhere between 2,314 millimeters and 2,316 millimeters. This is a range that the true value is in. And because, it's not exactly accurate to the 1 millimeter. I might move the tape measure a little bit, see it's a little bit longer or a little bit shorter. I could jiggle it, or I'm not sure if it's perfectly straight across the table or whatever. So this plus or minus 1 millimeter is probably around correct for this kind of measurement. Now, there is another way of writing down this plus or minus error or uncertainty. I could also, let me move this real quick. I could also measure this as, state this as 2,315 parentheses 1 millimeter. When I do this, when I put a number in parentheses here, it's an alternate notation, another way of saying that there's this 5 is a plus or minus 1. Okay, this last digit here is plus or minus whatever's in this parentheses. Let me give you another quick example here. Let's say I have a measurement of a different table that's 5.125 plus or minus 0.015 meters. Okay. Another equivalent way of writing this down would be 5.125 and then in parentheses 15 meters, right? So that's showing that these last two digits here are plus or minus 15, plus or minus 15 in these last two digits. So this is just another alternate way of writing down uncertainties. We will most typically be using this explicit uncertainty using a plus or minus. There is another type of uncertainty that's worth mentioning here, and that is what we call a percent or a fractional uncertainty. So, for example, I could have a measurement that says it is 2.83 plus or minus 0.03 meters. Now, I could, if I wanted to, write this down as a percentage. So I could say it is 0.03 divided by 2.83 and times 100. So that's about 1% here. So another alternate way of writing this down would be to say 2.83 meters plus or minus 1%. Okay, so I can write down my uncertainty as a percentage. One last example here. Let's say I have 6.2 plus or minus 0.3 kilometers, right? I can rewrite this as 6.2 kilometers plus or minus 0.3 divided by 6.2 times 100. It's going to be about 5%. 5%, just like that. Okay, so this is an easy way to write down your uncertainty, either using percentages or absolute quantities, just like this. Now, uncertainty is a very powerful concept, and explicitly writing it down like this is very good when you're doing experiments. But the problem is, for us, we're not doing a lot of experiments. We're doing more theory, right? We're thinking about how things work. We're doing a lot of exercises, and we don't always want to be carrying around double the quantity of numbers that we need to. And so instead, we're going to use a new concept called significant figures. And the idea with significant figures is that the number of digits that we write down implies our level of uncertainty. So it's kind of a shorthand, more streamlined way of implying our uncertainty without explicitly writing it down as a plus or minus. And this is just a lot easier to work with. And so we'll primarily be doing most of our future exercises using significant figures. Okay, let me give you an example of how this works. I measured the length of the table to be 2,315 millimeters. Now, what I want you to notice is that I did not have any digits here after a decimal point. I did not write down 2,315.1 or 0.2 or 0.5 or 0.0 millimeters. Why? Why didn't I do that? Well, it's because I could only measure up to 1 millimeter, right? I couldn't measure smaller than a millimeter with my tape measure, and so I just can't tell you what these numbers are because I can't measure it. These numbers here are completely uncertain. I have no idea what they are. And because I don't know what they are, I'm not going to write them down. Okay? And that's the key with significant figures. We try to only write down digits that express information, right? If there's no information, if I can't measure it, I'm not going to write that digit down. Okay? Now, I want to also look at this, and I want you to notice that this 2, I'm very, very certain about this 2. When I measured the length of that table, I could see clearly it is over 2,000 millimeters. And so this 2 has a very high level of certainty with it. I am very certain about it. This 3, also very certain. This 1, pretty certain. This 5, not quite so certain, right? Why? Because we said it was plus or minus 1 millimeter. And even if I don't write down plus or minus 1 millimeter here, The fact that this is my last significant figure, the furthest to the right, indicates that this has the least certainty in it, right? It could be a 6, it could be a 4, maybe it's even a 7, right? There's a chance. So I think it's around a 5. A 5 is my best guess, but I'm not completely certain about it, okay? So the idea here is that my level of uncertainty increases to the right until I get to this 5. And this 5 is the last number that I can have really any kind of information from. And after that, I reach this yellow line, which we could call my limit of certainty. And after that, to the right of that limit of certainty, all those digits are completely uncertain, completely unknown, and I don't write them down because I don't know what they are, okay? This is how we use significant figures, okay? What we say is the numbers that are significant, that have some level of information, we write them down. So let me ask you a question. The question is, how many significant figures do I have in this measurement? Well, let's count them. This 2, very certain. This 3, very certain. The 1, very certain. This 5, pretty certain. Has some information there. I'm not exactly sure if it's a 5, but it does carry information. And so I'm going to count it, and I'm going to say that there are now 4 significant figures. Okay, 4 significant figures here in this measurement. Now, let's keep going. What if I was now going to measure the width of the table, right? I'm going to measure the width of the table, but I'm going to use a different tool. For the length, I used a tape measure, accurate to a millimeter. For the width, I'm going to use a centimeter ruler. Okay, so there's markings every centimeter, but there's no millimeter markings. So I cannot tell you how precise to the millimeter any measurement is going to be. All right, so now I measure the width of the table, and I get a measurement of 82 centimeters. That's the width of the table. Okay, great. How many sig figs do we have here? Well, I think it's pretty clear. I measured an 8 and I measured a 2, so there are 2 significant figures in this measurement, okay? Now here's where things get a little bit tricky. What if I wanted to express this number in millimeters to match the millimeters of my initial length? All right, I want to keep it in the same units. Okay, well, in millimeters, this is going to be 820 millimeters. Now, how many significant figures are there? Well, I see 3 digits, but I know I did this measurement, and I did not write down 0.0 here. I could not do that because I can't measure millimeters. There's no millimeter markings on my ruler. And so that means I know that this 0 is not significant. And I know that these 8 and this 2 are significant, so I still have 2 significant figures. I could not measure individual millimeters, so there's no way I could keep this I could not assume this 0 is significant. In fact, this 0 is a placeholder. It does not represent any information. It's just there so that the numbers are in the correct place value. It's a placeholder, not information. And that is tricky because a lot of times we'll come up with numbers and there's a 0 or a couple of zeros at the end, and you're not going to know if they're significant or not. It's a little bit ambiguous. Likewise, I could take this number, and if I wanted to, write it in terms of meters. Well, what would 82 centimeters be in meters? It would be 0.82 meters. Now, how many significant figures are there? Well, it's the same exact measurement, right? So there has to be 2. That tells me that this 0 is not significant, right? So zeros in the front there are not significant. So zeros are kind of confusing. You know, that's the message that I kind of want you to get away from this. Zeros are confusing. Sometimes when I see them, they're significant. Sometimes they're not. We need a better way to write down numbers to indicate what's significant. What we're going to come up with is a system of notation called scientific notation. Okay, now scientific notation is going to come in a form where you have a number of some kind followed by a decimal point followed by some number of digits over here, and eventually you get a times 10 to the power of something. Okay, so in this kind of notation, it's important to note that this first digit, it's only one digit in front of the decimal point, and it's going to be either a 1 through 9. So there cannot be a 0. It can be any digit from 1 to 9, but not a 0. And then after that, you have some number of digits, and then it's going to be times 10 to the power of something. Okay, this is how we write numbers in scientific notation. Why? What's the advantage? Well, we have a few advantages. One advantage is that all the digits that are written down are significant. There's no ambiguity. If you see a digit, it is significant. And another advantage is that by putting everything in powers of 10, it makes it very easy to multiply and divide numbers together that are written in scientific notation, because you can just add and subtract the exponent on the power of 10. So it's a very, very good way of writing these kinds of numbers down. Let's go through a few examples of putting numbers into scientific notation. Okay, here's my first example. I've got 0.510. Now I want to write this in scientific notation. What does it look like? Well, it's going to be 5.10 times 10 to the power of minus 1. Okay, what I can see right away is that I've got 3 significant figures here because I have 3 digits written down and they are all significant. That means this 0 was measured. It's not a placeholder, it was measured. If it was just a placeholder, I wouldn't write it down, right? I wouldn't need to. It was measured. All right, let's try another example here. How about 12,078? What does this look like? This would be 1.2078 times 10 to the power of 4. Okay? Clearly, in this kind of scientific notation form, how many significant figures do we have? We have 1, 2, 3, 4, 5. 5 sig figs. And finally, one last example here. 0.0093. Okay, we write this in scientific notation, and we're going to get 9.3 times 10 to the minus 1, 2, 3. Minus 3. And here, it's very clear and very obvious to see that we only have 2 significant figures. No ambiguity. So scientific notation comes to the rescue here, and it always tells us exactly how many sig figs we have. Very, very clear. Okay, now at this point, I want to very briefly discuss some vocabulary, some words that I might have thrown around. And that's the difference between precision and accuracy. Okay, now in common English speech, we use these words to mean essentially the same thing. But in science, these words have 2 different meanings, and so we want to make sure we understand what they mean. Here's the idea. If a number is more precise, then what this really means is that it has more significant figures. Okay, it's quite simple. That's what it means. So for example, we have a number 0.51693 and a number 0.52. Which one is more precise? Well, this one is more precise because it has more significant figures, which means I was able to measure that number to a very precise degree, to a fraction of a fraction of a fraction of what I was able to measure here. Okay, so this is going to be more precise. That's precision. Okay, now, if we say something is more accurate, that's a slightly different meaning. What we're actually saying is that it is closer to the true value. Okay, so let me give you a quick example. Let's say that the true length of my table was, I'll just keep it in yellow here. Let's say the true length of the table was 2,314.8756 millimeters. And two different people go up to measure the length of this table. And one person gets a measurement of 2,315, like we did in the beginning. And the second person gets a measurement of 2,318 millimeters. Which one is more accurate? Well, quite clearly, one of them is closer to the true value. This one is, right? So we're going to say that this one is more accurate, okay? Now, they both have the same level of precision, but one is closer to the true value than the other. This other person here, maybe they made a mistake. Maybe it wasn't at an angle a little bit, so they measured a slightly longer distance. Whatever, they're less accurate. In science, we want high accuracy and high precision. That's sort of the gold standard. That's what we're trying to achieve. But precision and accuracy do mean two separate and different things. Okay. All right, now the last thing we want to look at today is how to do arithmetic with significant figures. Okay, so this is the last thing we're looking at today. And here's the idea. Let's go back and let me grab this, this table here that we drew, because it was such a good piece of art. I need to use it again. All right, so here we are. We've got our table. Now, we measured our length. We measured our width. We measured our length to be 2,315 millimeters. Now, here's the situation. What I'm going to do is I'm going to add a piece of tape onto this table, and I'm going to bend it around the edge, right? So there's going to be a little piece of tape here, and it's going to sort of bend around and go underneath the edge of the table there. And I'm going to say that it is 0.2 millimeters thick. Okay, that's the thickness of that tape. So now what I've essentially done is I've made the table a little bit longer because I put that piece of tape on the edge. The table's actually a little bit longer now. So the question I want to ask is, how long is the table? Okay, now that I've put this piece of tape on it, what is the new length for this table? Well, okay, let's do the math, okay? We've got table initial measurement was 2,315 millimeters, and now I'm adding an additional 0.2 millimeters right onto here. So what is this? Well, we add it up. We get 2.5132. Okay, there's my answer. 2,315.2 millimeters, right? Isn't that my answer? No, that is not my answer. This is incorrect. This is not the new length of the table. Why? Why? Because when we look at this first measurement, we saw that there was nothing here in the decimal place. Why? Because I could only measure up to 1 millimeter. I could not measure anything smaller than a millimeter with my tape measure. And so I have no idea what this digit is. I cannot assume it's a 0 and pretend that this is going to wind up being a 2. I don't know that. Maybe it's not a 0. Maybe it's something else. In fact, this 5 might not even be a 5. It could be a 6 or it could be a 4, right? Plus or minus 1 millimeter. It has the least amount of certainty there. And so I cannot tell you exactly what this answer is going to be in the tenths of a millimeter, right? This is now beyond my limit of certainty. And so what I have to do is I have to take anything beyond it and round it. And in this case, it's a 2, so I'm going to round it down. And so when I write my true final answer, it's going to be 2,315 millimeters. That is the length of the table that I am comfortable with. Now, maybe if I had 100 layers of tape, then it would add up to be an amount that I could physically measure with my tape measure, and it could be bigger. But with just one single layer of tape, it's too small for me to measure, and so I cannot just include that extra level of precision in my final answer when I didn't have that amount of precision initially in my initial measurement. So what this does is it gives us sort of a rule for addition and subtraction of significant figures. And the rule is basically that the uncertainty of your result is going to be limited to the term with the greatest uncertainty. Okay, so since this first initial measurement of 2315 has so much uncertainty in the tens place, I cannot honestly put a result here with a number in the tens place because that's just too precise. I don't have that much certainty. I can't write that in. All right. Now, let's take a look at what happens if we now want to find the area of the table. Okay, so what do we know? Well, we know that the length is 2315 millimeters, and the width, if I recall correctly, is, here it is, 82 centimeters, right? So if we multiply these two numbers together, we're going to get the area. Now let's say we want the area in meters squared. So let's convert everything into meters, and that'll get them all into the same units, which is kind of important. So this is going to be 2.315 meters multiplied by 0.82 meters. Okay, and what is that going to equal? Well, 2.315 times 0.82 is going to be 1.8983. Meters squared. But how uncertain am I about this final answer? Where is my limit of certainty? How many significant figures can I actually write down here for my answer? That is the question. I see that I have 4 sig figs here. I have 2 here. So how many significant figures should I have here? And the answer is 2. Okay, the answer is I am limited by the smallest number of significant figures that I'm putting in, and that's this one. But I want you to develop sort of an intuition about why. Why is it only 2? So let me show you sort of an example here. Let's say we're doing this math, right? It's 2.315 meters multiplied by 0.82 meters, and we said that that is equal to 1.8983 meters squared. Great. But the point is that this 2 right here is not super guaranteed to be a 2, right? That's my least significant number, and it could vary. Maybe it's actually a 1, maybe it's actually a 3. So what if we pretend it's a 3 and we pretend it's a 1 and we see how does that affect the final answer, right? Because we know that's our least significant digit. So what happens if it's a little bit off, if we're off by that 1 centimeter? Well, we do the math. Okay, let's do the math and see what the resulting products are going to be. 2.315 times 0.83 is going to be 1.92145. 1.92145, okay? And the other one's going to be 0.81 times 2.315, and that's going to be 1.87515. 1.87515. Square meters. Square meters. Okay. Now, let's look at these results here. What we can see is that the 1 is definitely significant, right? They're all agreeing in that first digit. In the second digit, we have an 8, and that's pretty significant. This one's an 8, this one's a 9, which is really close, right? Very close, so that's good too. The third digit here is a 9, and this one's a 2, and this one's a 7. Now I seem to have lost any kind of pattern. They're not close to a 9. It seems like maybe I could get any digit within that third spot there. I could get a 4, I could get a 5, I could get a 0 if I just make this difference between these two numbers a little bit smaller or a little bit bigger. So basically my limit of certainty is after these first digits. After that, I don't know what's going on. I don't know what numbers are going to pop up. But before that, I think it's definitely going to be a 1, and it could be an 8 or a 9 or a 7 or something close to an 8. But after that, I really don't know. So I only have 2 significant figures in my product. This is why I have 2 significant figures here. And the rule that we're going to write down for multiplication and division is going to take that into account. Okay, so we're going to say that the significant figures in the result are limited to the number of significant figures in the least precise term. Okay, so the fewest significant figures that are going in, that determines the maximum number of significant figures we can have in our result. And those are the rules that we're going to be using to do all of our math in pretty much all of our problems throughout this course for addition and multiplication, and how we take into account the number of significant figures that go in and come out, and the level of precision and uncertainty that goes in and that comes out. One last thing that's worth mentioning here is that I am rounding a lot, okay? Like these numbers here have to sort of get rounded off. So I have 1.8983. I see that I should only have 2 significant figures, right? So actually, I should round this product off to 1.9 meters squared. This should be the actual number I write down to 2 significant figures, and these numbers are going to get rounded up, because this is a 9 here. Okay, so I'm going to be doing rounding, but I only want to do it at the last final step. I want to carry through all of the high precision numbers until the very end, and then I round. So that's one last rule. You only round your final result to the correct number of significant figures. Okay, that's the last point there. All right, so we went over this idea of uncertainty. Sometimes we will explicitly describe it as a plus or minus some amount or some percentage, but most often we're going to be using significant figures where the number of digits describe how precisely we've made the measurement. And so the number of digits are going to wind up having an impact on arithmetic when we add, subtract, multiply, and divide, and how many digits are going to be in our final resulting answer. All right, it's a lot of information today. We have some exercises that you should do before we go over them in our next lesson. So please check the description below here for a link to a PDF on my website that you can download with some exercises and do them before we go over them in the next exercise. If you have any questions about today's lesson, I'll leave a comment below with your question. I'll try and get to it. And if you thought that this lesson helped you out, give me a like, give me a sub, and I'm going to keep going and giving you some more. So until next time, let's keep on learning, and I'll see you then. Thanks.